Hi, kids. Okay, hey, today, or at least right now, I'm going to talk to you a little bit about Newton's third law. This is one of those where I know we talked about this in the past, where hey, you probably memorized it, the words. If I was to start it and say, for every action, you would say, there's an equal and opposite reaction. But then once you start doing problems, you don't really understand it, or maybe you don't really understand it, and you start getting questions wrong. So Newton's third law, it seems really simple. For every action, there's an equal opposite reaction. But when you start applying it to real life stuff, it's a little weird and confusing. So let's talk about a couple different examples. So, this is a pretty. We'll talk about the car bug example first. So let's pretend you're driving along, and all of a sudden, a bug splats right on your windshield. And the question is, well, which one has the bigger force on it? And the answer is, duh, of course, they both have the same force, because for every action force, there's an equal and opposite reaction force. So let me just show you guys Newton's third law. One way you can write it is sometimes you'll see it written like this. The force of object 1 on 2 is equal to the force of object 2 back on 1. And sometimes you'll see it like this, a negative sign, just to show you, hey, it's going the opposite way. But it doesn't really matter if you put the positive or negative as long as you draw your picture. So that the forces have to be the same and they go the opposite way. Okay? So if we talk about the car and the bug, okay, well, what are the two objects? The car and the bug. So that means the force that the car exerts on the bug has to be the same as the force that the bug exerts on the car. And then the question is, well, why does the bug go and pretty much nothing happened to the car? Well, that has to do with Newton's second law, F equals ma. So if you think about it, so we have, well, the force of the car on the bug has to be equal to the force of the bug on the car. In the opposite direction, if you want to put a negative sign here, I would rather you just understand it, conceptually. So that means, hey, that if we do our F equals ma for each one, if that's the only net force acting on each one, for the bug, you get this teeny tiny mass. For this car, you get this gigantic mass. So that means for the bug, you get this gigantic acceleration, and for the car, you're going to get this teeny tiny acceleration. Which, hopefully that makes sense. I mean, can you imagine you're driving along and you hit a bug and all of a sudden you could feel your car slow down? That's a scary bug. So that should explain that one. Well, then how do we explain one of these other ones? So let's say you have a tug of war, okay? Two people are, having a tug of war, and you might think, well, geez, in order to win, I got to pull harder than the other person. And the answer is no. Because remember, you can't pull harder on the other person than they pull on you. That's Newton's third law. If I pull on you, you pull back on me with the same force. So then how do you ever win a tug of war? Here's the answer to that. I promise you guys, you can beat anybody at tug of war if all you do is put them on roller skates and you're on, like a nice smooth ground. Okay? You will beat them. I promise. No matter how much their mass is. Okay? And it's not because you're going to pull harder on them. Even while you're winning, you're going to pull with the same force. It has to be the same force. The reason that happens is you have to push or pull on something else harder than they do. So, for example, let's say we have our two people. Here's person number 1. Okay. Here's person number 2. And they are separated by a rope. Okay. If I was going to draw the forces acting on them, you would have, hey, person number 1, normal force, Fg. Person 2 is going to be more massive, Fg, normal force. And then I would have this tension force. These two forces have to be the same. Newton's third law. It's not Newton's third sometimes. It's Newton's third law. All right, so then those two forces have to be the same. Well, if this person is going to win, they accelerate that way. Well, if they accelerate to the right, then that force has to point to the right. So there has to be some other force acting on that person. Okay? And that force has to be bigger than the force of tension. In fact, because they're going to accelerate together, because they're kind of a system to hold it together, that means there has to be a smaller force than the force of tension acting on this person. Well, what is that force? You guys should know this. When you do tug of war, you get down low like this, and you push against the ground. And then by Newton's third law, the ground pushes back on you. So like this would be really the force of friction from the ground. Okay, that's how you're going to win. Okay, so the way you win a tug of war is you push harder on something else than that person is pushing on something else. But again, please don't make that mistake. Oh, I got to pull harder. No, you don't. It's not Newton's third time sometimes. Let's do another example. We'll talk about this one. Okay, this is another pretty classic one where it's like, hey, I got this set up. Ta-da! And then the question is, well, how much force does that thing exert? And a lot of people are going to be like, well, that thing's got to exert 10 newtons of force, because, see, there's 5 newtons going this way, and there's 5 newtons going that way. No! So, in fact, if the way you want to approach this, guys, is with everything. Let's draw our picture. Okay, there's my picture. But then I want to draw an FBD. So if I want to figure out how much force this is exerting, you can really think of it like 3 different pictures, right? You could say, hey, I got a FBD for that, I have an FBD for this, and then I have an FBD for this. For these guys, I have the force of gravity, which for both of them is 5 newtons. Okay, that's how much they weigh. Well, these guys are at rest. Therefore, the force of tension has to cancel out the force of gravity. Right? Yeah, it does, yeah. Because if it's at rest, no acceleration, no net force. These 2 forces have to be the same. Well, if you look up here, okay, this force of tension has to be equal to that force of tension, assuming, well, there is no rotation on it because it's just at rest. So, well, how big is that force of tension? It's 5, okay? Another way of looking at it, if you think about this free body diagram, what's supplying the force of tension? That scale is, how much force is that scale applying? 5 newtons. Now, it's true, okay, like there's also going to be a 5 newton force the other way, okay, but the scale is not going to read 10 newtons because the scale is only pulling with the force of 5 newtons. If it was pulling with the force of 10 newtons, then this guy is not in equilibrium. Newton's third law, not Newton's third sometimes. All right. Last example is let's talk about a rocket. Okay, so if I have a rocket that is accelerating up, as rockets tend to do when they take off, you might think, well, what's the force that's propelling it forward? Well, in order for that rocket to get propelled forward, it has to push something down, and that something that's being pushed down is going to push oppositely on the rocket up. Well, what is that going to be? That's going to be the gas. The rocket pushes the gas backwards. Action force. Reaction force is the gas pushes the rocket upwards. So if I was to draw an FBD for the rocket, so here is the rocket. Okay. There's my rocket. Okay, if I was to draw an FBD for that, you would have the force from the gas going that way. Well, what other force is acting on it? Force of gravity. And if it is going to accelerate up, the force from the gas has to be more than the force of gravity. Again, is there a force acting on the gas? Yes. Do I put it on this free body diagram? No. Because what is this? This is the rocket. So this is where you guys got to be careful. Action-reaction forces don't cancel because they don't act on the same thing. If they acted on the same thing, then they would cancel, but then they're not action-reaction forces. Another one that, let me do real fast, and then I will be done. If I have a person that is just standing there on the ground, okay, and you might be like, hey, what's the action-reaction forces for that person? Well, there's a bunch of them. Okay, you could do one action force, could be the force of gravity pulling that person down. Well, what's the reaction force? And some people are going to say, oh, the ground pushing up. No, it's force of 1 on 2 equals force of 2 on 1. So if we say, what are the 2 objects? The person and the earth, then Action force, force of gravity. Reaction force, you're pulling up on the earth. Well, am I going to draw that here? No, because if I draw an FBD, I'm not going to draw an FBD for the earth. I'm going to draw an FBD for the person. So like, there's the force acting on the person, force of gravity. Well, there's a normal force pushing up on the person, right? You better believe it. In fact, these two forces are equal, but they're not an action-reaction pair. Because if the action force is the ground pushes up on the person, guess what? Reaction force is person pushes down on the ground. I'm not going to draw that on my picture, though, because that dot right there represents the person. These are the forces acting on the person. These, they do cancel, but they are definitely not action-reaction pairs. All right. I hope that helps. Bye, kids.